that regions of uniform intensity are unaffected by smoothing. So the answer for this is that the coefficient should sum to 1. And the reason for that is that we don't want to add any additional energy into the system, basically. So we don't want to add any additional energy into the system. One way to think about it is, let's say that you have a signal where the intensity value is I at all the places, and now you multiply I with the coefficients of the filter, which is, let's say, WK. So the final value becomes summation WK into I, because I is the value at all the points, and you take the summation over K. Now, because I is constant, you can take it outside. It will become I summation WK. And when summation WK is 1, the final value also comes out to be I. So this is one way to check that the summation remains 1.
Okay.
That no additional energy is added into the system, basically. And yeah. So regarding the second part, so I think this one, so what you were supposed to do in this one is, yeah, I think the value was 114.7. Most of you have done it correctly. 1A1. So there was some concern in 1A1 and 1A2. So 1A2 was fine. So how do you calculate? So I think some of you might not have done this part. 1A1. So how do you calculate it? The way to do it is you write down the value of basically Gaussian. You write down the one-dimensional Gaussian distribution with sigma equals 1. It will be 1 upon root 2 pi exponential of x minus x square by 2. And now you equate this value to 1 by 1000 of the value of the peak of the Gaussian. The value at the peak of the Gaussian will be 1 upon root 2 pi exponential of 0, which is 1. So 1 upon root 2 pi. So 1 by 1000 into 1 upon root 2 pi. And you want to find the value of x. So one other way to do this is that what some of you did is that you evaluated the value at x equals 1, x equals 2, x equals 3, x equals 4. And you saw that at x equals 4, the value was more than 1 by 1000. And so you don't go to 4. You basically choose 0, 1, 2, 3. And similarly in the negative direction, -1, -2, -3. So the 7 points become -3, -2, -1, 0, 1, 2, 3. So these are two ways to derive it, two ways I can think of. And then you just have to calculate the values. Just put these things in the Gaussian distribution and you have to calculate these values. So is that clear to everyone?
Yeah.
Okay. So this is just applying the 1D Gaussian on the values in A. And then it says that what will be the smooth value of the pixel with intensity 118. So you use this filter and just apply the filter, and when you put the filter here, what will be the value? So you basically have to multiply these values and just put on top of that, and then it will become. So if you put it here, it will start from here till here, and you just have to then multiply this with this, 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 and sum all the values, and the final value comes out to be 114.67, I think.
Yeah.
And so the third part is, let me check if I have written the code for that. So some of you have written, yeah. So this is the code for the third part. You were supposed to write a little bit of code for it, write a MATLAB program to compute the smooth values for the entire row. You may want to use the MATLAB. So how can you use the con function to do this? So let's say that the sigma is 1.0. Again, we decided that x values will be from -3 to 3. And this is just the distribution. And this is the Gaussian distribution that we wanted. So exponential of minus x square, this is like pointwise product because it is a vector, upon 2 into sigma square. And this is 1 upon root 2 pi sigma. And this is the f that we have in this. I've just taken the f value into a variable, and this is the simple function that we have to use to do the convolution, to do apply that filter. Basically, out is equals to conv of f comma g.
Yeah. Yeah, so this is like something I was curious in, and I think it was expanded upon in the other questions after this, anyways. But when you apply the conv function, what does it do in the corners, like in the ends? Because yeah, when we're doing this, if we're doing it on like 118, then we've got enough values on either side for you to just calculate it, right? But what happens if you pick it on like, let's say, like on one of the corners or the other corner? Because then you only have like, because then some of your filter, some of that range goes is outside of your range, right? So like I don't know how conv deals with that.
So that is a good question. There are usually two ways to do it. One is known as zero padding. So what happens in zero padding? So because you are using MATLAB for this, so what you would do is that you will go on the MATLAB website and search for conv filter, and it will give you the configuration of how this conv filter particularly works for MATLAB. So what happens in such a case? So that is the way to find out how it works and what is the default configuration. Where, when there are multiple ways to solve it, there's one default configuration that MATLAB uses, and you can, if you want to use the second configuration, you can use that as well. So what happens in this is that they do something known as zero padding. So what happens in zero padding is, so like Matthew said, if I want to convolve this filter, I put this filter here. Let's say that I want to put it here, 0.399, I want to put here. Then all these three values won't have anything here to get multiplied with. So what zero padding does is that it puts 0, 0, 0 here, so that it can get multiplied with it. And it multiplies 0, 0, 0 with this, and this gets multiplied with this. So this is one way to do it. Probably this is what MATLAB does. So MATLAB will definitely have an option for doing this. I'm not sure if this is the default configuration in it or not. The other option is to just start from here, such that you start 0.004 multiplying with 46.
Yeah. Oh.
So basically, it depends on what is the output shape that you want. Yeah. So if you want the output shape to remain the same as the input shape, you will have to do zero padding. Otherwise, you'll lose some. So that is yeah. So is that clear to everyone?
I mean, yes.
Okay.
Yeah, I'm just curious about that, and because like especially I think later on the cheat sheet they ask about the secondary derivative and about how that helps you estimate the ends, and I don't understand that part. But yeah, I guess that's later. That's question. Yeah. That's question 3, I think. So yeah.
Yeah. Okay. Yeah. I mean, when we'll go there, we'll talk about that. So, so in question 2, so we are just saying that this filter will give you as an approximation for a derivative, and so we had to show we used to use a smooth row. So what it is saying is that the smooth row that you get out of this question, when you apply the MATLAB thing, do the MATLAB code and get the output, use that and find the first order derivative using this filter. So you will apply this filter on top of the output of this thing. So that will also remain a simple thing. Basically, let's say that the output of that was out, and my final output will be the conv of out with g. So g here is minus 0.50, which is basically the derivative filter that I have here.
Yeah.
So this second part in this question was, what effect does smoothing prior to differentiation have on computing derivatives? I think some of you wrote the right answer and some of you did not attempt or something like that. So, I mean, in simple terms, what you can say is that smoothing before differentiation removes the noise, so it removes the noise. So this is the original signal, and this is how the signal looks like. It's going up, down, up, down, up, down. There's a lot of noise. And then it goes up, and then again there is a lot of noise. So what happens is that if I directly take the gradient of this one, at this point it is pointing upwards. At this point the gradient will point downwards. At this point it will point upwards, then downwards. So the gradient will show a lot of turning points. These are known as turning points when the direction of the gradient, basically the sign of the gradient changes. So the gradient is positive, the gradient is negative, and we'll have a lot of false turning points. And similarly on this side as well, we'll have a lot of false turning points. But if I use a smooth signal, if I smooth it first, before taking a derivative, I smooth it. This is how my signal will start looking. And as you can see, there's just one gradient. The gradient might be a little bit different, but the sign will remain same, and you won't have a lot of turning points here. You won't have a lot of, mostly no turning points here. So the main turning point is just here, which you actually wanted to find. So this is the benefit of doing smoothing prior to differentiation. Is that clear? Does anybody have any concerns in that question?
No.
Okay. If anybody thinks that I'm going too fast, or you want some more clarification on a particular question, you can stop me and let me know. Let's go to question 3 then.
Yeah. Mm-hmm.
And so show that smoothing an intensity signal with a Gaussian and then differentiating the smooth signal is equal to. So in this, I think most of you did it correctly, let's say. But we can have a look at the solution too, but I think most of you did it correctly.
You could basically just bring the derivative inside, right?
Yeah. So that is what we wanted to exactly. So when you will write, this convolution can be written as an integral, and the derivative of an integral is equal to the integral of the derivative. Basically, you can take the derivative inside the integral. The reason is that an integral can be thought of as a summation, and let's have a look at the answer though. Yeah, so basically this is the form for writing the convolution. A convolution can be written as an integral g of x minus u iu du. So what now we are saying is that you can take the derivative inside the integral. Why you can, this is a property usually you should remember, but if you forget, how do you confirm it? Is that an integral can always be thought of as a sum. So basically it can be thought of as a plus b plus c plus d, and now you have to take the derivative over of all the, the summation. And the derivative of a summation is equal to the summation of the derivative. So you can take the derivative of all the individual terms and then take the summation. So basically you can take this inside, and now this was one single step was to take this inside, and this is the derivative. Now we'll apply the chain rule. So when we'll apply the chain rule, we'll see that this is basically, we don't even need to apply the chain rule. This is not a function of x. So you can take this outside the derivative. And then you will be left with iu, derivative of g of x minus u with respect to x, which can be written as g dash x minus u iu. And when you will, so this can directly be written as the convolution of g dash x with ix. So this is like the first part. And so the second question is that show how edges in an intensity function ix can be localized at the zero crossings of this. So edges in the intensity function are basically the extrema in the first order, in extrema in g dash x into ix. Yes, so they are like the extrema of g dash x, ix. And how do you find the extrema of a function? To find the extrema of a function, the first derivative test is like you take the derivative of that thing and put that to zero. So the derivative of, yeah.
What do you mean extrema? Do you mean when the derivatives are the highest, as in?
Yeah. So extrema of a function is either maxima or minima. So we want to find the extrema of g dash x into ix, which means when this function g dash x into ix is
zero.
The derivative is zero. So this function is maximum.
So you're saying like it's saying if you're maximum or minimum, if your slope's like really high, like really steep, is that?
Yeah. So if the derivative, yeah. So the edges in the intensity function occur when, you can think of it like. I think this is like good enough explanation that when it is maximum at the derivative, when the slope is the maximum. So basically when g dash x into ix, so you have to realize that we are now convolving with the derivative of Gaussian filter, basically. So when the convolution of the derivative of the Gaussian filter with the signal is maximum or minimum, that is where the edges in the intensity occur. and
Oh,
yeah,
okay. So that's what you mean by edges. So edges is literally just maximum slope.
Yeah.
Because I thought you meant like it's like on the corners of like your intensity function. So like the thing we talked about in part 1. Just
No, these are not those edges.
Yeah. Okay.
That is something. Yeah, these are not those edges. Yeah, these are not those edges. And because that would be more simpler, right? That would be your limit of x. If that is what those will be the corners, right? They will be like the lower limit of x and the higher limit of x.
Yeah.
That is something else.
Okay.
Yeah. So this concludes this part. And the third part is, suppose Ix consists of a step edge of height h. Derive an expression for the output of derivative of quotient filter acting on Ix, and some more things. So I have written the solution for this. Let's have a look at the solution. So people have done this in different ways. This is my way of doing it. I think this was simpler. So I hope everybody understands it. So this is a step function, which is basically Ix is equal to h when x is greater than equal to 0, and Ix is 0 when x is less than equal to 0. So it is basically like this and this. So it goes like this. So this is the definition of the step function. Now what we want to calculate is g dash x into convolution at Ix. So this can again be written as the integral, which is g dash u I of x minus u du minus infinity to infinity. So what there's a property of integrals that you can split the integral like this. That now I have split this integral into two terms. In the first part, I'll take the integration from minus infinity to x. In the second one, I'll take the integration from x to infinity. So basically, this is a basic property of integration, which is you can split the integration. So you have to integrate. You had to sum over all the values of x from minus infinity to infinity. I said that I'll do the summation in two parts. First, I'll sum over all the values from minus infinity to x, and then I'll sum over the values from x to infinity. So this is just one step. Now I've got a function here which is I of x minus u. So what will be I of x minus u looking like? So using this definition, I of x minus u will be 0 when x minus u is less than 0. So here, when the inner term is less than 0. So here the inner term is x minus u. So when x minus u is less than 0, which means when x is less than u, then this function is 0. And the other case is when x is greater than equal to u, this function is h. So now let's utilize this. So within this range, when u lies from minus infinity to x, u is from minus infinity to x. Basically, it is always smaller than x. So u is always less than equal to x. U is from minus infinity to x. It is always smaller than x. So in that particular case, the value of I of x minus u will be equal to h. So I just substituted that value. And in the case when u is greater than x, which is this one, greater than x up to infinity, the value will be 0. So I substituted the value 0 here. So this will become 0. This entire term becomes 0. Because h is not a function of u, you can take it outside the integral. So this gives you h into the integral. And when you write down this integral, this will become g of x basically. So just the Gaussian itself. So the final term becomes h into the Gaussian. And so this is the term, and there were some other parts in the question. The other part was show that the maximum response is at x equals 0 and the magnitude is this. So how do we find the maximum response? Again, there are like more than one ways to do it. So one way is to, when you want to maximize a function, you take the derivative of it and put that to 0, and whichever point is doing that, you use that. The other thing is that we know that this is just a Gaussian probability distribution. And for a probability distribution, the maximum value occurs at its mean. And we know that this is a zero mean Gaussian distribution. So the maximum value will occur at the 0, x is equal 0. So the maximum response occurs at x equals 0. How will we find this value? We'll just take the value of this function at x equals 0. So we put x equals 0 in this. This is what we get. Exponential of 0 is 1. So the final terms becomes h upon underscore under root 2 pi sigma square. So this is like the maximum response that we get out of this function. So does anybody have any questions in question 3?
No, I don't.
So yeah.
I don't.
So in question 4, it says that by using a Taylor expansion, derive determine 3/3 convolution mask for the following operations for the first order partial derivative, second order partial derivative, and this. So how do we go about doing it? It says that you have to use Taylor expansion. So I think most and all of you were able to derive it for all of these, but let's have a look. So basically, this can be derived by first writing. I think all of you were able to solve it.
Yeah.
Yeah, I think all of you solved it. So, but still have a look. So by using a Taylor expansion, determine 3/3 convolution masks for the following operations. Let me have just give me a second. I don't have it here, but yes, I sent it to somebody. So this is how you do it. So I have taken a Taylor series expansion around x. So I'm writing the value f of x plus h is equals to f of x plus the first order partial derivative into h plus 1/2 h square, the second order partial derivative, and I have left out the higher order terms. Why I have left out the higher order terms? Because we are looking for an approximation here. And similarly, I write the expansion at x minus h, which becomes f of x minus h equals f of x minus partial derivative into h plus half of h square into second order partial derivatives. Now what I do is I just sum up these two things. When I sum up these two things, sum up the LHS and sum up the RHS. So when you will do that, this is what you will get, f of x plus h plus f of x minus h. And these terms will get cancelled. On the right hand side, you'll have 2 times f of x. So I take it on this side, it becomes negative. So this is what I have on this side, and on this side it will be h square into the second derivative. H square is taken here. So basically the second derivative is written in terms of f of x plus h plus f of x minus h minus 2 times f of x. So now let's have a look at the answer once. And so basically this can be written as, so we derived the second order derivative. It was written as f of x plus h plus f of x minus h minus 2 times f of x. So this is the form for the second order partial derivative. Similarly, you can derive it for the second derivative in terms of y. And if you want to do it and get the first order derivative, so you have to think, how can I use these two equations to get the first order derivative? So for that, you'll subtract the second equation from the first equation. So when you'll subtract the second equation from the first equation, the second order derivative term will get cancelled and you'll be left with the first order derivative term. So that is how you derive the first order derivative, this and this. So now let's have a look at the second one, the third one. So the third one, delta square, this can be written as the summation of these two partial derivatives. And you just have to now sum up these two matrices. And when you sum up these two matrices, you get this answer. So this becomes the solution for the third part. So the B part is by considering the Fourier transform of a box filter and Gaussian filter, explain why an image that has been filtered is more likely to have high frequency artifacts than one that has been Gaussian filtered. So by the way, Fourier transforms are very important. So Fourier transforms are like not so common in images. They are somewhat common in images, but for audio, they are very common. So like every audio signal is usually the first step for processing it as fast Fourier transform. So, I mean, fast Fourier transform is a technique to compute the Fourier transform very quickly, and it is very widely used. For example, I think up to 2 years ago, or maybe still now, every audio that you give to Siri or the Amazon thing or to Cortana, the first thing they do is that they apply a Fourier transform, which is why it is very important to understand it. So now the question is, by considering the Fourier, so you have to consider the Fourier transform for box filter and Gaussian filter and have a look at how it looks like, basically the behavior. So here I have plotted both of them. So this is the when you apply it on Gaussian, and this is when you apply it on box filter. So the difference between box filter and this one is that the box filter still has some peaks because of the sine C. So it will still have some peaks and some dips and peaks and dips, whereas this will just be tending towards 0. So it is because of these peaks and dips that you will be able to get some signal out of this. So some signal will pass through these peaks and these peaks and these peaks, which is why it will have more high frequency artifacts. The box filter
but isn't it? But like I thought, both of them they deteriorate exponentially, anyways, right? So,
Yeah.
so they still decrease. So even though you have peaks, the peaks are smaller and smaller, right? So
Yeah.
why is it that those peaks are more particularly like more problematic than just the other one of just having like constantly like decreasing?
So both of them are constantly decreasing, but one of them has peaks. Like if we have a look at this function in particular, this one is just going to 0. But what the other one is doing is that, so the mean in terms of mean, its value will be decreasing. But what it is doing is that it has some values above it and some values below it. Some values above it and some values below it. So if you can think of it as like, let's say that the value is 1 here and -1 here. So if you'll multiply 1 with something, it will let something pass away. And -1 will also let something. But what this will do is that this value is 0.1 or 0.2 as compared to 1 peak, basically. So 0.2 will not allow that much of the signal to pass through.
Yeah.
So it is true that both of them are decaying, but this one is decaying with peaks, which allows some of the artifacts to pass through.
Yeah.
So the last one was write a MATLAB program to read in an image and compare the action of a box filter to a Gaussian filter. So this is like, so I haven't written the line for reading the image. So for reading an image in MATLAB, you use a function called imRead. So you'll first read the image. So somebody was asking, how do you set the all these values for?
That was me, because because I understand like how you do it in MATLAB, but it's just how do you come like what do you mean like the same spatial scale? I don't understand what that means.
Yeah, that's a good question. I think it will be something like by trying it out and having a look at the form of the two functions, how they look like.
So
that is how. Yeah.
So are you just supposed to just keep on trying it until they're both kind of the same level of blurriness?
That is one way to do it. Other way is to just take this function and first visualize it as it is.
What do you mean?
So before applying it to an image, you can just plot these two functions separately and have a look at how they look like. That is one way to do it. And the other way is just like you said. And the third way would be to compare the form of the two functions for the different values of these things. Before even plotting, just compare the values, hit and try what will be the scales for these two.
Yeah.
So this is like, so if you think of it like the box filter is 6, which means it will go from 6 to 6, like both in both directions, 6 this direction, 6 this direction. And if you think that the Gaussian with this thing might also behave similarly in that fashion. So that is one way to compare it. It's not like there's a theoretical way to write it down very properly, which could be done by for checking on certain values of the function. Let's say you check on certain values of x. You decide that I'll take 5 points on x-axis, which will be 1, 2, 3, 4, 5, and I'll compare the values of these two functions on those 2 points and see whether they are similar. But other than that, this is just by guessing and taking a look at the function form.
Okay.
Yeah, it's not like if you had taken 32, it will be wrong. It will also be very similar. So.
Yeah. So when the question asks like compare the action of a box filter to a Gaussian filter of similar spatial scales, what do they want you to say? Because like I did it, and it's just both pictures came out looking like a bit blurry. So I don't understand compare the action. So what's the difference then?
So I think one of the case would be to take an image where they will be helpful. So if you'll take an image which is already very good looking, there is not a very good chance that they'll be able to do something. But you might want to take an image which is susceptible to the noise that these filters are able to take out. So if you take such a noise, basically, if you'll go to the lecture site, you'll see when are these filters used. So you find an image which has that kind of noise. So you just show that, I applied this filter because it has this noise. This filter to this image, this has this noise. It was able to remove it. That is like what you are taught about this filter, and you can do everything for the other filter as well. Yeah, just showing in practice what they have written in the slides about these filters.
Okay. Because I just used like a random image I had and just.
That won't do much because it is already probably very good looking image. So these might just make it bad. So this is like a fifth question. Does anybody have any doubts till question 4? If not, I'll go to question 5 then. Okay. Yes. Yeah. Did you have any doubts?
Oh no, please go on to question 5.
So in question 5, so the question is that the first part is quite interesting. The first part is that two images have the same histogram. I think some of you didn't answer it correctly. So two images have the same histogram. Which of the following properties must they have in common? So the answer is that the total power and the total entropy will remain the same, whereas the pixel-to-pixel correlation will not be the same. So let's have a look at the answer once.
Yeah.
And so I've written two answers for it, but let's have a look at the shorter one first. So the shorter one is that because the first two things depend on pixel intensities and not on the order of arrangement. So let's say that you have one image. What you did to that image is that you jumbled up that image. You took the parts of the image and put them at different places. As soon as you will do that, you will know that the pixel to pixel correlation won't remain the same, because the part that was here in the second image, it has gone to that part.
Oh.
Although both of these images have the same histogram, it has the same image. I've just jumbled it up or shuffled it around. So this part will definitely change. The question is, will the sum of squares of pixel values remain the same? Yes, the sum of squares of pixel values will remain the same because the pixels remain the same. I've just changed the place of the pixel. So the sum of squares of pixel values. Similarly, sum of I log I will also remain the same, because I log I is just a function of one pixel, and I'm summing over all the pixels. So it does not matter where I put the pixel. As long as I'm summing over all the pixels, this will remain the same. So this is like the first explanation. The second explanation is this. I tried to write it down in terms of math and have a look how it will look like. So let's say that IP is the intensity of pixel P. I am denoting the intensity of pixel P as IP. And f of IP is any function which is a function of the intensity of pixel P. So it is only dependent on the intensity of pixel P, not on the pixels near it, just on the intensity of pixel P. This is any such function. And this is the sum of that function over all the pixels. So my claim is that any such function will remain the same for the two images. So any function which is just of this form, that it is summing over all pixels, the function of intensities at each single pixel. So how do I go about proving it? So what happens in histogram is that on the x-axis, you have a bunch of intensities, and on the y-axis, you have like the number of percentage of pixels who have that particular intensity. So let's say that these are the intensities that I have, which is I1, I2, I3. I1, I2, I3 to IN on the x-axis. These are the intensities that I have. And with P of I1, I'll denote the set of pixels with intensity I1. So for a given intensity in the histogram, you have a number of pixels which are there, or a percentage of pixels that are there for this intensity. What I'll say is that Pi1 is, let's call that set of pixels Pi1. Now let's go back to our sum. So we are interested in this sum, which is a sum over all the pixels. So you have to sum over all the pixels present in the image. What I'm saying is that instead of summing like this, I will sum like this. I'll first sum over all the pixels which have intensity I1. Then I'll sum over all the pixels which have intensity I2. So all the pixels which have intensity I1, basically the set Pi1. Then I'll sum. So basically, I'll sum the first row over the first row of the histogram. Then I'll sum over the second row of the histogram, and so on. And so why can I write it like this? The reason I can write it like this is that in this way also each pixel is counted once and exactly once. So every pixel is counted because every pixel will have a place in the histogram, and every pixel is counted only once because it will either have intensity I1 or it will either have intensity I2. So this is how I write the summation. This is for the discrete case. If you want to generalize it to the continuous case, you'll have an integral here. So now what I am saying is that let's have a look at this particular term, one particular term. Within this particular term, so my claim is this is like the summation over pixels with intensity I1, f of I1. So f of I1 will remain the same for all the pixels within that intensity because it is only a function of intensity. It is only a function of intensity. That is why this function will remain the same for all the pixels with that intensity. So I can take this out, and because I'm summing, so this will be the number of pixels with intensity I1 into f of I1. Similarly, number of pixels with intensity I2 into f of I2. Now, because in the two images, the histogram is the same, so the number of pixels with intensity I1 are the same. and function of intensity I1 will also remain the same because I1 is same. So my claim is this term individually will be the same for both the images. Similarly, this term will be the same. Now, because all the individual terms will be the same, so the summation will also be the same for both the images. So basically, this term will be the same. So this is another way to write it down. Although, I mean, it depends which one is easier. I thought that this one might not be so easy to convince to some people. That is why I wrote this one down. But I hope it is clear. Okay. Oh, so the second question is that a basic histogram equalization is applied to image A, and this results in image B. Why is that so bad? I think, yeah, so for this we'll need a good understanding of what histogram equalization does. What it does is that, let's forget about histogram equalization for now. Let's say that any image that I take on my phone, it has a lot of pixels, it has a lot of color values from RGB. Within RGB, many different types of reds, many different combinations of reds and greens and all sorts of color values. And there's something known as levels. So when I have to store this image, I'll be able to have 2000 levels. So I'll have 2000 different levels for storing colors. So what happens in a normal RGB image is that it allocates equal number of levels or the same number of levels to different colors, basically. So some levels are allocated for light red, some are allocated for orange, some for red, some for all different varieties. It allocates the same number of levels. That is how a normal image works. But what we want to do in histogram equalization is that, let's see what we do. So what happens is that let's say that I take an image which only has blue color in it. And now what I want to do is that I want the blue. So within blue, it has a lot of variations. So what histogram equalization will do is that instead of having all the 2000 levels for different colors of reds, different types of oranges, it will try to allocate these levels within blue itself. So it will give more levels to light blue, and within all the different possibilities of blue, it will give more and more levels. So this is what histogram equalization does. It allocates more levels to certain things. Let's see what it will do in this case. So in this case, in this image, a lot of pixels, I think 60-70% of the pixels are this grayish, light gray, white color, the one outside the coin. And very few of the pixels, let's say 30% of the pixels are dark gray or black. And what happens in histogram equalization is that when I do a histogram equalization, it will take all the levels that I had previously for all the colors, it will take 70% of them and it will allocate them to a single color. It is almost there's literally no variation within this color, very small variation. So it will allocate 70% of the levels to this, and it will allocate 30% of the levels to black, dark black, basically. So what happens within that is that although initially the black was having a lot of colors within it, I was able to allocate a lot of levels. Now it only has left with 30% of the levels. So with 30% of the levels, you are not able to see a lot of variation within the black thing, and it compresses the black color. But within white, what happens is that you have allocated so many levels for white that there are not even so many ranges within this color. So it stretches them out, basically, which is not possible. So that is why it starts to look very bad. The stretchy lines come within it. So that is why it starts to look very bad. And how do you fix it, basically? So I'll say that I'll do two different histogram equalizations. So I'll take a histogram equalization for the gray color, and I'll take histogram equalization for all the colors present within this coin. So when I take a histogram equalization for all the colors present within this coin, I'll be able to see all the variations and it will give a good contrast. And similarly for the back. So this is one of the solution. And some others have written a way is to use gamma filter, and that's also good. I mean, that's also a good solution. So both the solutions.
What's gamma filter?
I don't know what you call what it is called in the slide, but it is in lecture 1. So like exponential of gamma, something you multiply it with that. I don't know what. I don't know the name of that filter though.
Okay.
It's in lecture 1 if you want.
Okay, yeah. I'll look into that later then.
Yeah. So that is one other way to do it. Let's go to question 6 then. In question 6, so now we have to derive what will happen if x is changed to ax. Basically, now we are working in a two-dimensional case, and we'll multiply our x vector with a matrix. A is a 2 cross 2 matrix now, which is here known as 2D linear transformation matrix. A lot of linear transformations can be written in this form, and they will be multiplied by ax. And part B, we'll see that rotation can also be written as a matrix multiplication. So what happens that if you do this transformation, how will the Fourier transform change? So we start by writing the definition of the Fourier transform. So the two integrals, one of the integral is over x, the other integral is over y, and this is just the form. So now what we do is that we substitute x with ax. A is the matrix, and this is the substitution that we perform. And now we will say that we'll call ax as x dash. So x dash equal to ax. Now what will be dx dash into dy dash? So by performing a little bit of calculus here, we'll be able to write dx dash dy dash as determinant of a dx dy. So now we'll use this form within this. So I'll substitute dx by dy as dx dash by dx dash dy dash by determinant of a. So I just done the substitution. What else? So I had x here. So I write that x as, so if I do left multiplication with a inverse in this term, it will be a inverse x dash is equal to a inverse ax. A inverse a will become identity. So I'll have a inverse x dash is equals to x. So that is the substitution that I'll do here. So by doing that, and ax is x dash, as we talked before, this is the form that we have come to. And so next step is to write this as this. So how is it written like this? Is basically there's a property that if you write. So one way to do it, what I would recommend is to write down A as a matrix A, B, C, D, and take U vector and take X and write down the form. And then when you write it down, you'll be able to see that you can bring A here as A transpose. So basically it will become A inverse transpose into U into X dash. So then basically you can take A inverse transpose U. So the final form will start to look like this. And this is how you do this part. And so the second part B within this question is that there's rotational symmetry. So what happens in rotational symmetry is that so what happens in rotational symmetry is that, let's say that A is a rotation matrix. So there are certain properties. I think it is in your lecture slides that you were shown how to write a rotation matrix in terms of cos theta and sin theta. So you can write your rotation matrix in terms of cos theta and sin theta. When you do that, there are certain properties that will come out. The first property is that the determinant of A is 1. So that is one of the properties. The second property is that A inverse transpose is equals A. When A is a rotation matrix, A inverse transpose is equals A. So we'll just use this formula because A is a linear transformation matrix. We'll use this formula for the final form, and we'll use these properties that we have just derived. So A inverse transpose can be written as A. That is what I'll do. And then next I'll substitute determinant value as 1. So I'll end up with f of u dash is equal to f of au. So this is the final form for the rotation. And this is question 6. Now going to question 7, the convolution theorem for functions of a variable. So I think most of you did 7a correctly. I can check the sheet once, but I think this derivation might just be in your, most of you did it correctly, might just be in your slides as well. So prove the convolution theorem. So convolution theorem is also actually quite useful. It is quite fundamental. So the some things which are very fundamental within this tutorial sheet, one of them is Gaussian distributions. So Gaussian distributions are very important. I mean, so most of the people in statistics, most of the statistics is, based on Gaussians. You can model every distribution as either Gaussian or the mixture of Gaussian, or there's something known as Gaussian processes. So I mean, if you don't know the form of any distribution, you assume that it will be a Gaussian or a mixture of Gaussian. And if you don't know the form of noise, you assume that it is Gaussian. And if you want to do something probabilistic, you want some probabilistic values within something, you put Gaussians there. So Gaussian is very fundamental within within science and engineering. The other thing that is very important is Fourier transform. This is because of a lot of applications. And the third thing which is very important is convolution theorem. So this convolution theorem is also quite important. So A part is clear. Let's go to B part, show that the consecutive series. So the second part is show that the consecutive smoothing with a series of Gaussians, each with a particular standard deviation sigma is equal to a single convolution. But I'm not sure if I wrote the answer for this, but this seems quite, it's not very difficult. Basically, I think most of you have done this correctly. And you just multiply them, and in the end you will get so if you use the convolution theorem, you will see that it becomes multiplication in the so because of as a consequence of convolution theorem, it will become a multiplication. Then you will multiply two exponentials. The terms on top will go into summation, and that way you will be able to write it more clearly. If you want, I can show the answer, but I think most of you already did this correctly.
Yeah.
Yeah, basically it becomes a sum in the Fourier domain. And so the third part is smoothing of a 2D image involves a 2D convolution with a 2D Gaussian. Show that this can be performed with two 1D convolutions. I think this also most of you did. I think all of you did this correctly as well. Oops. This is the answer for this. And basically, it's straightforward. It comes out u squared plus v squared, and then you can split both of them. Then they become two different Gaussian filters. And so that is like two one-dimensional convolutions. So the question is, what are the advantages of performing two 1D convolutions instead of a 2D convolution? I think some of you had some issues with this one. So the advantage is basically, I think most of you wrote the correct answer. So the advantage is computational complexity. It is computationally very cheaper. So it has some computational benefits. So one of the places where this is, there is in lecture 1. So it is shown in lecture 1 as well. They split two-dimensional convolution into two convolutions. So it is more beneficial when you have a bigger image. Let's say that you have a convolution filter of 3x3. If you'll just be convolving on an image of 3x3, it won't be very beneficial. But if you have a bigger image than 3x3 and you have to do a lot of convolutions, then this kind of splitting is very useful because you'll first perform 1D convolution and you'll save the values that you get. So you'll have to save the matrix and then you'll perform the second 1D convolution. So the computational complexity is very different. The difference is, 2D convolution might be k square, so order k square, and 1D convolution will be order k. So that is quite a big difference in computational complexity, but it comes at the cost of having to save the matrix, which in intermediate matrix after 1D convolution. So sometimes that is not preferable. And so convolutions are very important. Nowadays in AI, everything uses convolution neural networks. So everything is based on convolutions. And like whenever your iPhone is recognizing your face or anything, all of them are using convolution neural networks. The last one was also, I think all of you did correctly. There might be something, and I think all of you did correctly. So the last one is, so there are two things. First of all, you have a focus blur, and again, focus blur is modeled by a Gaussian. So if you don't know how to model anything, you model it with a Gaussian. Usually Gaussian model works very well for most of the things. And then there is a motion blur as well. And you have to write the spread function h of x, y and compute the Fourier transform. So, and use the result that Fourier transform of a Gaussian is this. I think most of you did it correctly. And in the second part, there was something basically so this is the final. I think all four of you wrote it. All three of you, the three I checked, were able to write it correctly. This was the final form. And then there is a Wiener filter. So this is, I think, from your slides again. So this Wiener filter, this is the form, and all three of you wrote it correctly. And so now this k is usually assumed that you will know the value of this k constant. So this is some of the questions that some people were having in the previous tutorial. How do you know the value of this k? So this is usually assumed that you know the noise function within this, and yeah, you don't have to worry about it. Basically, you will, whenever you'll use it, you will usually be having this value in practice. So yeah, does anybody have any questions?
So what's the Wiener filter actually do? So if you have a bunch of noise and you put in like a value of k, it could get you back like the image before the noise. Is that?
So let's have a look how the Wiener filter works. But I mean, it is only useful for certain kinds of noises. And k, you don't have to worry about it, but in practice, people have to worry about k. What they do is usually, let's say that you're working with one particular camera and all the images that are coming out are from that particular camera. So you know what time that this camera is doing this kind of noise. So you are able to identify with hit and trial that this is the kind of noise that you have. It's not like something that works on all kinds of noises. It is particular for some. I mean, yeah, it is useful for certain kinds of noises these days. So, yeah.
Okay.
Mm-hmm.
So in practice, you basically just like adjust the value of k and then find out the one that looks the most like desirable.
Yeah, that's one way to do it, basically.
And
I mean, that it would require. Sorry, yeah, go on.
how are they gonna examine this in the examination?
In the examination,
Yeah.
that I don't know. That's a good question. Some students were asking yesterday as well. I don't know much about the examinations, but so now they have formed a new channel on Teams for the B14 where all the lecturers are present, and I would suggest that you should ask this question from them. I mean, don't think that whether I should ask or I should not ask. I would suggest that if you have any questions, ask them politely the format for the answer, question paper, because it's not just you. A lot of students have asked me this question, and I'm assuming that students are asking other tutors as well. So a lot of students have the same questions. Feel free to ask the lecturer about the format for the question paper.
Yeah, because a lot of these questions, it seems like pretty hard for you to ask in the middle of an exam, kind of.
Yeah, I think you should ask